So we finished the last example where we had this phase angle and we had the current and the voltage not in line with each other, they've gone out of phase. So let's see how we can correct that problem. So with this, we've got the same circuit before. This time we're going to put an inductor in as well. So the idea is to use this inductor to correct the power factor and to get it back to normal. So we've just got the resistive element and we've not got the effects of the capacitor or the inductor. So the idea is, like we had before, we got this diagram, we saw it from Pythagoras really, when we got a phase angle happening here. This is Z and this is our angle. So what's happened is here, our normally just resistive circuit, this phasor has been rotated counterclockwise. So the way to get it back in line, to get the phase angle back to zero again, so it's just the resistive element, is to rotate it clockwise. And the only way to do this is to create a force, not a force, sorry, another phasor here, which is a mirror image of the one on top, which should allow it to rotate it back this way. So we end with just a line across here with just the resistive element and current and voltage lining up, and we've got a complete power factor correction. Now for this to happen, this has got to be a complete mirror image. Well, resistors is the same for both elements. The only difference is this height here is XC. So to have the same height here, what we're saying is that XC has got to equal XL, and this is XL here. Now the formula we have for XL, remember our formula for XC was 1 over 2 pi FC, and basically what this means is that because this is inversely proportional, as frequency increases, this gets more like a short. Basically its resistance value in ohms, its reactive capacitance, drops as frequency increases. So it becomes more like just a direct short as frequency increases. And it would approach zero resistance or zero reactive capacitance as F tended toward infinity. Now an inductor is the opposite of this. XL, we have the formula 2 pi FL, where L is inductance. And that's measured, capital H, in henries. Frequency is the same as before. This isn't inversely proportional, it's directly proportional. And actually, if we think about it, an inductor is just a coil of wire. Well, if you're passing DC through here with zero frequency, it's just a wire. There's no resistance at all, unless the resistance of the cable itself. But there's no reactive element to it because it's just a wire. And at very low frequencies, this acts like a direct short. And as frequency tends to zero, XL tends to zero. But as frequency tends to infinity, tends to higher, this acts like a complete short, like it's, a complete open circuit, like it's completely blocking any current flowing through. If you're a mechanical student, the analogy for this is that it's like inertia. It resists the change of voltage. It doesn't like changing voltage. So as frequency tends to get higher, so does XL. So what we need to find is a value to make XL equal to XC. Well, we can do that because we know that in this case that XC equals XL. We already know the value for XC. We worked it out up here. It's at the frequency we're looking at, is 67.72 ohms. And that's equal to 2 pi FL. Now if we rearrange that, we'll get to get L on its own, we divide both sides by 2 pi F, we get L equal to 67.72 divided by 2 pi F. That equals, obviously where F is 50. So that equals 215.56 millihenries. So that's times 10 to the minus 3. It's pretty unlikely that you'll be able to find a 215 millihenry inductor, but if you did this in the real world, you'd be looking to get the phase angle close to 0. You wouldn't be making your own inductor at 215.56 millihenries. You'd be looking, maybe if there's a 220, go for that and see what value it gives you. It will probably be very close. So, with a 215 millihenry inductor, XC and XL will equal each other. They'll be 0. So what does that mean for our formula? Well, before, when we worked out the amount of current in the circuit, we said that it was equal to V over Z. Well, at the minute, the way we worked out Z was equal to the square root of R squared plus XC minus XL squared. Well, in this case, if these two are equal, that cancels out. And the square root of R squared is R, therefore Z equals R. We're back to Ohm's law again. And so current is actually equal to voltage over impedance, but impedance in this case, when we've got resonance or XC and XL equal to each other, then it's going to be equal to the voltage, which is 240, over the resistance, or Z in this case, which is going to be equal to 100. So that will be equal to 2.4 amps. The phase angle here, obviously if we're looking for the phase angle, these two are going to correct each other out, so the resultant is going to be 0. You have 0 phase angle. Let's have a go at simulating this. So, in a simulation again, let's draw the circuit again. This was 240 volts. And it was 50 hertz. We had a resistor. Okay, so we've wired that up now. And a good test for this is going to be current. What's the current flowing in the circuit? Let's do a simulation. So, auto to trigger it to make it stay stable. So current flowing in the circuit. You see on one side of the wave here, because we're only going from the peak value from 0 to the peak, it is 2.4. We're not seeing quite the top there because it says 2.39, but it is going right up to the top there. So we've got the current we thought from our calculation. Now we can have a look at some voltages across different items. So let's put some voltmeters in. This time we're going to label them up though. So I put all three of my voltmeters in. This one is going to be measuring, I'll call it V res for voltage across resistor. It MultiSim Live doesn't like funny symbols or spaces in here, so make sure you just use something that's and this is going to be capital V cap, voltage across the capacitor, and then finally here we've got voltage across the inductor, so VIN, not V, I'll call it V in actually, so otherwise V in can mean something else. And then each of these are obviously going to be referenced to the ground state rather than putting a reference value in. So we're going to put in references. So copy, another reference, copy, another reference. We can leave these as refs as long as we know that VRes needs to be referenced to ref1, V capacitance needs to be referenced to ref2, and V inductance needs to be referenced to ref3. They all should be reading correct now. That's okay. So here we're seeing, the good thing about having it labelled is as well, it's okay seeing it on the other schematic, but when you come to your graph, you're not going to know where your probes have been placed. So it's good to have actual labels on them. So we've got VIND there for the inductance, VRes and VCap. PR1 is the current, it's got I and then V1. So we can't actually see that because I imagine it's in phase with the resistor at the minute. So what have we got here? We've got our, as we see here, the dark blue, VCap and VIND are 180 degrees out of phase. So when the inductor voltage is at absolute minimum, the capacitance voltage is absolute maximum, and they're symmetrical, so they cancel each other out. They will do. And what that means is that we're just left with the voltage across the resistor. And if we look there at the top, total, the maximum voltage across the resistor is 240, which is the supply voltage, which means none of it technically is being dropped across the inductor or the capacitor.